All right, can I have an audio check, please? All right, it appears to be working. So hello everyone, my name is David Rock. I'm here at the University of Maryland in Baltimore, Maryland, and welcome back to Cytometry NR. So today we're doing one of our bonus walkthroughs, covering the more extensive version of the downsampling and concatenation lesson, specifically focusing in on the concatenate function, which had multiple moving pieces as well as multiple nested functions. So it was on our to-do list to record. So now that we're in the summer and I have a little bit more additional time, I'm just going to go ahead and go through these different recordings, make sure I get all the videos so that they can be posted alongside the website. So this walkthrough is an extension of the Week 10 lesson, additionally documenting the steps via which concatenate function was assembled from start to finish. This walkthrough is entirely optional. It is not something that you would require in order to still follow along with the course, and has just been separated out entirely from the downsampling lesson, mainly in the desire to try to avoid having those who are already struggling to learn with functions from burning out due to too many examples too quickly. If, however, you want to see additional examples of how a more slightly complicated function is crafted, or really just enjoy learning about FCS file internals within R, then this walkthrough is very much for you, and you should feel free to continue following along. So, in the journey thus far, at this point in the Week 10 lesson, we had just wrapped up creating the downsampling function. While downsampling by itself can be useful under certain circumstances, it is more often used as part of a workflow where those downsampled outputs are combined together into a single FCS file, i.e. concatenation, for use in unsupervised workflows like dimensionality visualization. So unlike downsampling, which works within an individual FCS file, and then you can iterate through each of those one at a time, if our goal is to build out a concatenate function, we'd want to first iterate through every FCS file to retrieve the needed downsampled outputs, then combine them together before finally outputting them as a new FCS file. So while nesting downsampling within concatenate to create a nested function is a simple enough process, in practice, the tricky part is that when we concatenate FCS files together, we typically want to add keywords that allow us to distinguish within the concatenated file the original FCS file from which each cell arrived. So for FCS files, these keywords end up being integrated in as additional numeric columns within our exprs matrix, which results in the need not only to modify the expr slot, but subsequently additional modifications to both parameters and the description slots before we're able to create the new FCS file. It is because of all these numerous moving parts that showing the full walkthrough for how Concatenate was assembled within Week 10 was just not feasible, and why we have resorted to sharing the fully assembled Concatenate function and its various nested helper functions within the R folder for that particular lesson. That allowed us to have the focus remain on the actual implementation of the workflow, and not so much how the sausage is made when it comes to the function internals. However, if you have not yet burnt out from function building, this walkthrough documenting the process via which Concatenate was created can be seen below. So, setup, seeing as this is a portion of the original walkthrough, i.e. the index.qmd files within the GitHub repository, it has now been relocated to its own separate .qmd file, concatenate.qmd, which we'll need to reload in, as well as the additional different components that had been previously assembled, so that we can replicate the working environment's contents that had been present at the time before I ended up splitting everything into the two respective projects. So let's first start off by assuming you had completely shut down Positron, reopened it, and you just need to start entirely from scratch. So let's go ahead and first reattach the required R packages to our local environment via the library call. And these will be the Flow Workspace, the Flowgate package, the dplyr package, ggplot package, and the per package. Next up, we would then need to reestablish the file path to our current data folder, which is what we've been doing throughout the course. If you keep the organization scheme that we've been following, it would just be a data folder directly below your working directory. We're assigning that to this object variable storage location so that we're able to use it again in the future. And then at that point, we just proceed to load in our saved gating set from downsample via the load_gs. As you may remember, we saved this as a little intermediate file, which is being denoted by that .gs at the very end. So wherever we had saved it to, we just need to re-specify that file path, and then we can just go ahead and save it directly to what we've been using for the name, sfc_gating set. And sure enough, once we load in our already assembled gating set, we can see that yes, all those gates did survive the transition. We still have them present, and we're able to use them if we so wish. So finally, where we left off, we had the downsampling fully assembled, the downsampling function fully assembled in our environment. Since we'll need it when it comes time to building out the concatenate function, we can go ahead and source that final version of the downsampling function that had been stored within the R folder at the end of the week 10 walkthrough. The source function in R is basically the equivalent of calling library on an R package, but it works at the level of an individual R file, returning the generated contents to our local environment. So this is what you'd see in this case. So if we had copied in the R folder from that end of the week 10 example, we could just go ahead and specify the file path within it for the downsampling function, which is stored as a downsampling.r file. And then at that point, after having created the path, if we source that file path, we'll end up having downsampling become active in our working environment. And that would be something we would be able to visualize in our right secondary sidebar. So at this point, we would have reassembled everything that we would have previously had and would need to be able to continue to create the concatenate function. So if you remain interested, please continue with the walkthrough below. If, however, you got here by mistake and you really just want to go back to the week 10 material and just see the big, broad overview, the link is there for you as well. So with that, let's go ahead and get started. So first off, when we are going out and trying to create any kind of function that's going to be even moderately complex, it's good to have a sketch out a plan of how to do so. So overall, our broad goal is to take the FCS files that are currently within our gating set, use our newly constructed downsampling function to retrieve a desired number of cells from our target gate, and then combine these together to form a concatenated.fcs file that we can then use downstream for unsupervised analysis. So with the downsampling function already written, the initial components needed for a concatenated function are ready to go. So we just need to be able to get those individual outputs back from our gating set, which we could do through iteration through the use of the map function from the perf package to get to those outputs. We would then need to figure out how the actual concatenation code is supposed to be implemented, after which point we could then reutilize the flow core package's write.fcs function to export out our combined together file as a new FCS file to a designated folder location. So, as we're sketching out this mental plan, it is the middle-late section that we can anticipate encountering some additional complexity and therefore additional troubleshooting that will be required. So previously when we've been working within downsampling, we were simply swapping in place the original Xpers matrix with a smaller Xpers matrix, while trying to keep all the other components of the original FCS file intact. When we concatenate, a new keyword column typically gets added to the Xpers matrix, which allows us to distinguish for each cell the original FCS file it came from before everything was concatenated together. This new column also permits us to gate a group of cells of interest, and by visualizing the keyword on one axis, be able to separate out on the basis of these groupings. So because this new column is located within the Xpers matrix, it needs to be numeric. So it can't be a character and it can't be a logical type value. So if our metadata / keywords are character values, we'll need to convert them over to some form of a numeric-based keyword value, while also providing the means to back-translate these numeric values to their original character form, likely by adding the new keyword within the description / keyword slot so that it can serve as a dictionary-style lookup when we need it in the future. So, consequently, as we saw back during week 3, the simple addition of a new column to the Xpers matrix means we're going to need to add entries for it in the parameter data frame slot, as well as potentially the description keyword list slot. This means that from the very get-go, we will need to mess around with more FCS file internals than what we did when we created downsampling if our goal is to return a fully commercial software-compatible FCS file. So before we getting started, it's worth remembering that this is just one approach to writing a concatenate function. So this is the one that I happen to have formulated. However, there are other ways to write a concatenate function, and as long as you still end up with the same result, none of these different variant ways is wrong. So as with everything in R, there are multiple routes that one can take to get to these outcomes. You're also still very much welcome to extend, modify, alter the existing code beyond what we're showing in this example so that it better fits your own requirements going forward in the future. So let's talk about nested downsampling. So let's first start off by creating a skeleton for what our new function is going to become. So it's been a few weeks since week 10, so if you think back to what we were doing, since concatenate will need to work/orchestrate things at the level of the entire gating set, we're going to use, for one of our first function arguments, GS as our first argument. So what this would look like as we start to assemble, we have a little bit of a Roxygen skeleton, just to let us be able to have some documentation about what we're actually doing. So in this case, we give a description, so concatenates together FCS files that are present in the gating set on the basis of a given name. At that point, we can designate what that first argument is through the use of the @param part of the Roxygen, in which case we first provide the name, which is going to be GS, and a short description, so a gating set object. At that point, since I've designated this as my first gating set argument, within the little function parentheses, I'm going to go ahead and put GS. And as you may remember, when we're creating a function in R, the function parentheses, when we put that assignment arrow at a particular name, that name becomes the name of the function that we're going to be able to use. And at this point, the function is just everything that's within the little curly brackets. At this point, we haven't built it out yet, so I'm just going to put a placeholder, which is being hashed out, so it shows up as a comment within our actual code. So, however, we're not just trying to combine entire FCS files together. Rather, we're really trying to combine cells that are present within the same designated gate together. So we can go ahead and provide a subset argument, as well as copy some of those elements of the Roxygen skeleton that were documented in downsampling so that we don't have to rewrite the same documentation over and over again. So if we're going to go ahead and we add a new function by placing it within those parentheses right after a comma. And then I'm just going to go ahead and grab that same Roxygen argument for subset with the description of what it does, which had been present in downsampling. I'm just going to copy and paste it in directly below where we have for param. So speaking of, the line of code we ran to retrieve our downsampling outputs would likely be one of those first lines of code that we're going to need to run within our concatenate function. So similarly, like we already had that which we were using to test downsampling, let's just grab that line, repurpose and modify it inside our actual new function that we're creating. So a couple things that we need to do is we need to make sure that the arguments that are provided to this line are also accounted for within the concatenate's functional arguments so that they can be able to match with each other and that they follow our recommended documentation. So Lucia, it would probably be dependent on files that are acquired on the same instrument platform. So if I had data from one Aurora with the same laser configuration as data from another Aurora, you would be able to concatenate those two files together. However, if it's on a different type of Aurora platform with different lasers that would have different detectors, then no, I would not be able to combine those together. In a similar situation, if I have data from a Sony instrument and I have data from an Aurora, I would not be able to combine them just because the internal slots are just going to be so dramatically different. If you're trying to do that kind of a combination, you could try doing completely just extracting out the expers matrix and then combining them together in that manner. You would want to try to basically minimize all the additional metadata, parameters, descriptions that would be mismatched between those instruments and just try to combine equivalent data. You would need to probably tinker on the column names to make sure they are the parameter for one channel on one instrument matches the parameter of the channel for the other one. So a little bit more complicated across the board. And then, as far as the auroras, your question, the question is, can you combine data from both the conventional and spectral mode for aurora? They are saved in slightly different ways internally for the FCS file, which is going to be the complicated factor. But if you're trying to merge them after the fact, you could basically do the same thing as your spectral flow cytometry file. You could just downsample, you could just select the equivalent columns that would have been the channel markers for the conventional file, and then try to combine those two. That's one possibility of, if you're trying to do a complete mismatch of things, trying to bring them together under a similar roof. And then once you have those combined into a broader concatenate file, you could try wrapping them in some kind of metadata. So it's definitely something you can tinker with and try to experiment with, but it's possible. It's just a lot more of moving pieces around. All right. So within the function, as we started looking at how to actually make these changes, let's see what we need to do. So we're basically copying in and running that first line of code that had been present for downsampling. So what this is going to look like is something like this. Let me double check here. Yeah, just need to make sure all the names are matching each other. So basically, downsampling already was pretty well fleshed out in terms of all these additional arguments. So we can just go ahead and copy in that line of code of the Roxygen skeleton itself. So as you can see, we have inverse.transform, downsample count, and add-on, and storage location, and return type. All these different arguments that are part of our downsampling function itself. So then once we have these guys, what we can just do is scroll down, having copied them all in. And as you can see, we are still doing some of those dependency documentation through the use of the @import_from tag. In this case, we're saying we're going to be using the per package. We need to use this map function from the per package. But then the line of code that we used to have for week 10 for the downsampling run, you see I'm just basically placing this in here, where we're iterating through the use of a map in per to be able to go through all the individual contents of our gating set. And then we're designating this is going to be passed to the downsampling function. And then all the different arguments that are being passed to downsampling are also here present. So all in all, this would iterate through. It would downsample for a particular target number of cells for a particular target gate within that gating set. And then it would return these as, in this case, a flow frame object, which would all be cobbled together, each item of the iteration as part of that overall list. So for that reason, I'm going to go ahead and name this object variable that we are getting back the flow frame list, just as we start our initial movements. So with these initial changes now made to our concatenate function, we can then go ahead and update/refresh it in our refresh the function that we're creating in our local environment by just rerunning the function code in its entirety. So there's two ways there you can go about doing this. One, if you're running things in Cordo, if you're running things in Positron or RStudio and it's present within the code chunk block, you can just rerun that code chunk so it will refresh all the contents that are made available. Alternatively, you can just highlight that line of code, hold down either Control or Command and Enter, depending on if you're a Windows or Linux or a Mac OS computer, and then that would just basically rerun the lines of code that are present. The main idea is as you build out the function, you want to refresh the function as it's being perceived by your working environment, just so that as you make changes, you know they're actually reflected by what you end up seeing if the function gets called, not the previous version that was more intermediate that didn't have all the new pieces that you added in. So typically, I will, as I'm building out my functions, set them up within a code chunk directly below. So let me try that again. So typically, when I'm building out my functions, I have them both a code chunk, a code block that will have the function code itself that I'm able to quickly rerun, so it refreshes in my local environment. But directly below that, I will have another code chunk that will just have like the output line needed to run the function I just wrote. So that way, my actual progress as I build out the function is I will write what I need within the internal part of the function I'm creating, run that code block so that it refreshes the function with those changes into my environment, and then run the code block directly below it just to see if I get the expected output from those changes that have been made. So what this would look like in terms of a output line, for example, is this one here. You can see I have my new function I've created, which is concatenate. I have the different arguments that are being put back in here. You can see I'm basically targeting our CD4 gate. I want to add on the name underscore CD4. I want to have 2,000 cells that end up being downsampled per specimen. This is all being returned for values. So after I refresh my function, I would hit that line. If it comes back correct at that point, I know I'm good to go. If all of a sudden I'm getting back errors, I know whatever change I made to my function as I was building it out ended up breaking something in the system and needs to be adjusted again. So in this case, you can see if I'm only grabbing the very first entry in terms of number of rows, that is 2,000. So I am getting in that flow frame list and seeing that, yes, it was properly downsampled. So we have successfully been able to make sure to integrate in the downsampling function so that we're able to retrieve flow frame objects from our gating set as they get iterated, and they're all combined together into a list that we're actually then able to use. So that part, as far as our initial changes to Concatenate, are been successfully implemented. So at this point, we have what is now a nested function. We have our big function, which is Concatenate, and underneath that we have the layer that is our downsampling function. So we have a function within a function, so a nested function. So at this point, if you remember, for our downsampling function back from week 10, we had it set so it could do return type arguments that would return various style outputs, namely FCS files, flow frames, which are the FCS file version within R, and then as well as the different data frames, which would just show us the underlying values within the experts matrix. So we could add an additional return type argument to both the concatenate function, but then we could basically set it up internally where it could do a conditional, i.e. one of those if or else statements, so that depending on what argument we provided to the main function, it would either return to us an FCS file, a flow frame, or a data frame, depending on what we were trying to get back. So what this would look like in practice is, once again, we just need to make sure we provide documentation saying what is the expected arguments for return type. So you can either provide it as between quotation marks, FCS, which would be the default, or a flow frame, or a data.frame as far as those individual arguments. And then at that point, you can see here within our function itself, we generally don't want to have to write out extra characters that we don't necessarily need to on an everyday basis. So you can see we're specifying out the default argument that would be provided, which we can supplant if we wanted to, but in this case we just say, let's have the preferred return type be the flow frame version. So at that point, working inside our function, we're just modifying what we previously had. So we're adding this conditional statement, which, if you remember, is basically if the particular values that are within the parentheses come back as true, then the lines of code that are between the first set of curly brackets would then be evaluated. If, however, the values that came back in here returned a value of false, then it would skip over this first section of code, and it would go down to the next conditional part of the statement, in which case it would run everything after this else, so these lines of code here. So what we'd have in this case is, if the return type argument was set to data frame, it would then end up running these two lines of code, which, as you can see here, our return type argument is set to data frame as a default for these two lines. So that's what we'd end up running, and that's what we'd end up returning. And that would be returned to the data frame list object variable inside the function. And then vice versa, if it's not a data frame, this would be evaluated as false. It would proceed to the next one, and then it would just return to us our default, which would be the flow frame style object. And that would end up being saved to flow frame list. So with these edits complete, once again, we want to make sure anytime we're building a function, we didn't accidentally break anything in the process of doing so. So let's go ahead and rerun the function's code chunk just to make sure the function gets updated within our working environment. And then we can go to the output line code chunk directly below, run that output line just to make sure we're getting back what we're expecting when we provide the different arguments. So if we go down to our output line code chunk, it's going to be something like this. So when I set it to return me a data frame, let's see what happens when I run this code chunk. You can see, sure enough, I'm getting back a data frame style object, which is what I expect. So at least for that first part of a code, we didn't end up breaking anything important. Let's go ahead and then switch for our output chunks return type argument. Let's switch it from data frame back to flow frame, just to make sure it's still able to return to us flow frame objects. So we go back over here, change our return type argument within this output code chunk, hit run code chunk or whatever you would see for positron in RStudio. And if we check it, sure enough, we now are able to get back that flow frame object. So no matter how we set that return type argument, we're able to return whatever format we're interested in terms of our working components. So our conditional statement, all those changes we made within Concatenate were correctly implemented, and we are now able to proceed. So at this point, within Concatenate, we are able to retrieve either lists that contain data frames or lists that contain flow frame objects. The length that corresponds to basically the number of specimens that are present within our gating set. So ultimately, regardless of what return type we get back, we will want to end up mutating a new column to the individual expers matrices that are contained within each of these lists, and append the corresponding metadata keyword that will basically allow us to pinpoint the original FCS files that an individual cell came from once everything gets smushed together, gets concatenated together. So while both return types will provide us the expers matrices, using a flow frame means that we can still have direct access to the FCS file associated metadata, something that the data frame option would not permit since it's lost all that additional context. So at this point in building the concatenate function, we have reached basically a fork in our coding path with a couple options to decide between before proceeding down one of them. So if we chose to go the return type equals flow frame for the individual flow frame, returning to us individual flow frames, we could dive back into those flow frames and retrieve out internal description / keyword lists for keywords that are of particular interest in us that would help delineate out the differences we would see for cells that came from one specimen versus cells that came from another. We could then also retrieve the expers matrix, append on the designated keyword as a new column via the mutate function, and then subsequently after that point where all these expers data frames have been modified based off of that internal keyword, we could then combine them all together, either using a function like rbind or from the dplyr package bind_rows to create us a more complicated combined data frame. This concatenated data frame would then be the object that would be passed on and ultimately converted into an FCS file, similar to the steps that we employed for the downsampling function. Alternatively, though, if instead of a return type being a flow frame, we went with the return type equaling a data frame route, we would have already retrieved out via the downsampling function those individual expers data frames for each specimen within our gating set. We wouldn't have access to additional metadata at this point in the stage since we would need to, so in that case we would need to separately retrieve out keywords for each specimen from that same gating set object we had passed to downsampling, and then somehow, some way combine the retrieved keyword values into the already extracted out data frame for the corresponding individual. So at that point, we could then append it as a new column using the mutate function, at which point the process would be very similar, if not identical, to what we saw in the last steps described when we were doing the return type equals flow frame. Namely, all these individual modified data frames containing unique identifying keywords would get concatenated together and then ultimately passed down and created into a new FCS file. So, as you can see, depending on which approach you took, you could still end up in a similar place using either of these approaches, but you would need different steps to be able to actually go about and implement your choice in order to get there. So this is a very typical scenario when it comes to coding your own functions, which is why I wanted to highlight it rather than just simply picking one and telling you that's the one I ended up picking. So ultimately, I decided I was going to go ahead and use the return type is equal to data frame approach. The main reason for this is that even though there are more steps involved, since you need to link already extracted data frames to corresponding keyword values that you need to retrieve again from the gating set, it is relatively easy overall to update a gating set's metadata. It's something we've done quite frequently throughout the course, namely, you run pdata on the gating set, you assign the output to a particular name, you have the data frame, you can update it, and then you can pass it back to the gating set to update the metadata. So in terms of if there's a value that you don't already have in your gating set, but you want it integrated in so it gets present when you concatenate everything together, that is a relatively easy task to go ahead and do. Vice versa, when you're doing return type is equal to flow frame, you're kind of restricted to keywords that are already present within those FCS files. Or subsequently, you'll need to write additional code to then afterwards allow external inputs, which would pretty much be rewriting the same code that you would have written anyway if you had taken the return type is equal to data frame option. So for that reason, rather than have to rewrite the same code twice, it's just easier to, in my particular implementation, to just go the return type data frame route and then just try to make sure you're correctly matching with the corresponding metadata as it gets retrieved. So, seeing as we've seemed a little committed to going the return type equals data frame route, let's first go ahead and see what existing metadata is present in our gating set as currently stands. So, once again, if we run pdata on our gating set, we assign the output to a object variable. We're going to go ahead and call this current metadata. If I just check the column names of our data frame, you can see there's only a single column, namely the name column. So this is very standard for what I associate with gating sets. We can then repurpose code we first encountered back in week 7 in a way of being able to update the metadata for a corresponding gating set. So, if you may remember, this particular example was using some of the data from the early part of the course. So we did have some metadata in addition to what we already had in the file. Namely, this was condition, infant sex, and the HIV exposure status. So this was present in one of those external CSV files that we could add in. So, seeing as both current metadata and the additional metadata data frames share a common column, which would be namely the name column, it is theoretically possible to combine both of these data frames together on the basis of that shared identity in form of the name. The way you would be doing this would be through the use of the dplyr packages left join function, which will merge both of them together on the basis of that shared column. So one thing we need to do is we need to make sure we need to update the row names, since gating set objects expect there to be a row name, and in the case of a recently brought in data from the CSV, there is none yet at that point. Then at that point, we'd then be able to update the metadata that's present in the gating set. So what this looks like in practice is we're going to left join both the current metadata, which is just that name column, and then the additional metadata with the other interesting bits of information. And we're going to do this on using the shared common column name. At that point, we get a larger metadata frame with containing all 4 of those columns. At that point, we can just go ahead and update the row names, which is what's needed by our gating set. And then at that point, once updated metadata is correctly formatted, we can just overwrite the existing metadata that's present within SFC gating set. And then if we output, we can see there's a name column, but then we also have condition, infant sex, etc. So at this point, our gating set now has updated metadata containing additional keywords that we can use to classify our specimens. Because of this, we have the potential to incorporate up to 4 different keyword columns in our future concatenated file. We can use name, we can use condition, we can use infant sex, or we could use the HIV exposure status. So as we set up to write our function code, one thing we should try to avoid is hard coding the column names in. So we don't want every function to work on a condition that on the assumption that your column is called condition, or that your column is called infant sex. Ideally, what we'd want is the ability to iterate through the metadata column names so that regardless of what they're named, the individual keyword column, whatever the individual keyword column is named, or if we have 1 keyword or 20 keywords, they all get correctly handled and they all get integrated into our final FCS file without the need to write additional lines of code. So, as we've committed to the return type equals data frame approach, let's go ahead and remove within our concatenate that conditional statement we had written earlier, instead only keeping the data frame option code lines. At that point, we could just rerun the function the function's code block, and then run the output code block directly below it, just to make sure any of the changes we did when we removed the conditionals are not impacting our actual ability to get an output. So sure enough, if we are updating our code block, we're getting rid of the little bit of conditionals, the if and else statement. We're only keeping the data frame list in this particular example. And because I want to have a good output line that tells me, is this working as I'm expecting, yes or no, I'm going to go ahead and take this data frame list, pass it to the length function, so then that way I know it's actually iterating out for every specimen within our gating set and not being something artificial abbreviated. So sure enough, at that point, if I run it on our gating set, you can see it's iterating through 3 specimens that were originally present in the gating set. So at this point, we have set up the code that we need to retrieve the metadata. So at this point, we will need to set up the code that is needed to retrieve the metadata for our subsequent data frame integration. Since we may not want to integrate all the metadata columns that might be present into our concatenated FCS file in terms of keywords, we will need to provide an additional argument basically saying subset for these column names. These are the ones we're actually interested in. These are the ones we actually want to incorporate. So let's call this new argument that we're going to create desired columns using the camel case for columns. And then at that point, we just add this in to our function, which is going to be located within those parentheses, and update the corresponding Roxygen documentation so we know what this new argument actually does. At that point, we can modify that very last line of code to a print function, just to return to us the actual names of the columns that are being used, just so we can validate those internals are working correctly. So looking at that in actual implementation, as I scroll down, you can see I've updated the Roxygen to give me a little reminder for future me 3 months from now what desired calls actually does. You can see I have not specified it as a default, so this is an argument that will be expected to be provided. And then at that point, I have not yet integrated it into the actual code itself, but I'm just making sure it's actually being seen internally by just printing it back to the console window at that point. So at that point, if I refresh my code, and then I run the code output, what I should see is just the names that I have specified in terms of the column names. The names I've specified to our desired calls argument being returned to me at this point in time. So with this done, let's just go ahead and retrieve the gating set metadata via pdata within our function as we're building it out. So as this is going to return to us as a data frame object, we could then subset for those columns of interest, which we're using via the desired calls argument, upon the basis of the dplyr select function. So since we're passing in a vector of external character strings, we can't just use select by itself with placing desired calls in the middle. We're going to have to wrap it in one of the tidyselect packages functions, the all_of function, just to avoid a warning message about changes in tidyverse behavior for what's happening. So what this would look like actually in the implementation is going to look like this. So we haven't changed any new arguments. Everything's still the same. So no changes for that part of the Roxygen skeleton. What we do have is several new functions that are being used internally. So we want to make sure these are correctly accounted for within the Roxygen. So we're doing import from biobase for pdata. Dplyr, we're using select. Tidyselect, we're using all_of function. So we are specifying all these as we go. So once again, we're just trying to grab the metadata. So we're first running pdata on our gating set. Gating set is matching the name argument that we're using externally. So yep, that should go in correct. Once we have metadata, we're basically subsetting it down to only be our columns we specified via desired columns. So at that point, we need to make sure it's select and then all of from tidyselect. And at that point, instead of the full metadata, we only have the metadata columns that we actually want to integrate into the FCS, the concatenated FCS file when it's all said and done. So at that point, I just want to go ahead and print desired metadata because that's the most recent thing we tinkered with inside the function, just to make sure everything is working as we're anticipating. So at that point, as it's very familiar at this point, you refresh the code block chunk of your function just to make sure it's active. The newest version is active in your environment. You run the output line directly below, and sure enough, we are getting correctly all the different columns we expect to see when we run we provide these arguments to the desired columns. And just to go ahead and make sure it wasn't a fluke, if I end up just providing 2 column names, basically subsetting it just for name and for condition, you can see I just get back these 2 columns, not the entirety of the metadata that's present for our particular gating set. So our lines of code appear to be working, and this wasn't a fluke. So at this point, Concatenate will basically go in, extract the metadata corresponding to our gating set. Each of these rows will correspond to an individual specimen, with each keyword column being a value that we will want to ultimately append into the specimen's expert slot data frame as a new column when the time comes. So, however, at the moment, our data frame list object within Concatenate is a list of data frames. So our main task before proceeding is to figure out a way for each specimen. We'll need to isolate out the respective row of metadata from that data frame, desired metadata, and then take those values and append them as new columns on to the already existing data frames for the expert's object corresponding to that individual. So, how's that actually going to work? So, since we're going to need to be able to do this on a per specimen basis, and we want to be able to pass not only these values from the metadata that need to be appended on, but then also the actual data frame to which those new values will be appended on as new columns, there's 2 things we need to work with at the same time: the metadata row and the data frame. So this is one of those situations where it's easier if we just go ahead and write a new smaller helper function that's able to do these steps and return to us a single object. So let's go ahead and create this new function in its own little code block. We'll go ahead and call this the keyword append function after its intended purpose. So from the current internally generated variables or /objects within Concatenate, it is likely that this one was going to need to have at least tree starter arguments to begin with. So x, which is basically the iterated in specimen name that we're going to use to filter the metadata data frame for the correct row. Y, which is the simultaneously iterated in expert's data frame that corresponds to the individual specimen. And then the metadata data frame, the overall broader one, that's going to be used to isolate out the named row for that particular specimen. So that sounds a little convoluted as I said it out loud. So let's actually see what this looks like in practice. So for our initial function /roxygen2 skeleton for this new helper function, it's going to look something like this. And for my little helper functions, those that would never really be seen to the outside world, that all are being used internally, I'll often just go ahead and denote that in the actual roxygen skeleton, saying it's the internal for XYZ function and what purpose it does at that point. And then I'm just going to go ahead and create those tree arguments and going ahead and placing them right here as well. And as you can see, this is just a skeleton function. There's nothing actually written yet, so a little placeholder note right there that's been hashed out just so it's not interpreted as code. So with these arguments in place, we can start figuring out how to tackle the first of the 2 moving pieces, i.e. the things that are being iterated into this new helper function. So x, which is going to be the specimen name that's going to be used to filter the metadata so that we get the corresponding values for that specimen. And to be able to do this, let's just go ahead and write an initial line of code within keyword append that would look something along these lines. So once again, x is going to be the name that gets iterated in, which will be use our metadata to isolate it out. So in this case, as we are putting this thing in, as we are starting this helper function, let's go ahead and make sure that the metadata data frame doesn't have any row names. So we can do that in base R by just setting row names in the metadata and then just overwriting them to null, meaning they're going to be empty. And then at that point, metadata should be just a data frame. So we can pass the data frame through the pipe to the filter function from the applier. At which point, for the column name, let's go ahead and filter for the value that's present in X. So if this column for the name was David, it would filter for David, if David had been assigned to X. If the value being iterated in by X was Sandra, it would search for the row that has Sandra present in the name column, etc., etc. So at that point, this filtered down version of the data frame would then be assigned to the add this row object variable within working environment of the function. So at this point, add this row has that single row containing just the keyword columns that we had selected, i.e. via the desired calls argument in the previous view, that we would want to be integrated in as new keyword columns. So at this point, we've successfully iterated in the single row component that ultimately we want to append to the data frames of expers. So at that point, we tackle the second moving piece, i.e. the second iterated in argument, the y argument, which will be those expers data frames that we have already isolated through the use of the downsampling function. So remember, within Concatenate, the list of expers data frames is currently being contained within that data frame list object that we had created within the first couple lines. So each object in a list is typically being displayed between square brackets, so it'd be square brackets 1, square brackets 2, depending on how many specimens you have in the gating set. So when we iterate .x is equal to data frame list, it's going to be the equivalent of if we ran x is assigning to x data frame list square brackets 1. So to help troubleshoot things that are being iterated incorrectly and not accidentally ending up one level above or one level below in that nested list, I'll typically assign them to an internal variable once they get there, just so I'm able to troubleshoot. So since we're iterating in these expers through the use of the y argument, we could save the y argument once it's internalized as a new variable called df, just so we can be able to check it through the use of the print function. So what this looks like in practice, as we are iterating in y, which are those expers data frames that are present in that list, this little internal object, we can assign it to df, and then we can return df just to make sure it is actually being seen correctly and that it's not being misinterpreted, and we're just getting still back a list object. At that point, we can run our function code just to refresh it in our environment, and then we can run the output line just to make sure everything is working out. After checking that data frame is indeed a data frame, which can be done via the str function, we could then proceed to combine in the isolated row that contains those desired keywords as new columns for this particular data frame. So the way you can do this is basically using the pliers bind columns function. So since add this row is just a single row, and our existing data frame contains many number of rows, basically the number of cells we ended up downsampling, the use of bind cols works basically by duplicating that single metadata row we have all the way down however many times to match the corresponding number of rows within the df argument. So let's see this in actual practice. So all of this is what we did. We brought in the iterated in expers data frame. We brought in our metadata and filtered it down just to match the name being designated by x. At that point, the data frame and the iterated and the metadata are correspondingly matched to each other, which is what we want. So we can combine them together to make the expanded out data frame that now contains those keyword columns that we actually want present for when everything gets concatenated together. And then at that point, since we have created this value as expanded data, we can just specify this is what we want returned to our previous function through the use of the return function here. So at this point, keyword append function has carried out its task, and we have now an expanded data frame that contains the new keyword columns. So we just need to be able to integrate this now completed helper function into our already present concatenate function. So for keyword append, we are intending to iterate in two separate arguments, x and y. X where it corresponds to the name of the specimen that's used to filter for the corresponding row in the metadata. Since we have not yet generated a vector of specimen names for this task, we can go ahead and do this by basically pulling the current existing metadata name column so that we end up with a vector of names. So let's see what this looks like when we start adding it inside Concatenate. You can see we selected for the columns that we were interested within metadata, ending up with desired metadata. One of those columns is still going to be called name, so we can just go ahead and pull the contents, which will become the file names. So at that point, this is going to be a vector style object. So if we refresh our function and run it, we would see that accordingly. So now that we have that vector for file names that can be passed to x, as well as a list of data frames, the data frame list object that can be passed to y, we're basically set up to be able to iterate. So if you remembered our main iteration package, the per package, map only really iterates over one single argument at a time. So consequently, if we want to iterate over two particular objects in a time, we're going to need to use the variant, the map2 function, which is able to handle simultaneously iterating through both x and y arguments. So what this is going to look like in process is basically to actually be able to run the keyword append function within our concatenate, we're going to structure it something like this. So as I scroll down, you can see I've now added map2 additionally to our import from tag within the oxygen skeleton, so that when it comes time to run the function, it's able to track back to where it's supposed to be at. All this rest of the line of code is very similar to what we already had. No changes have been made. But when it comes time to iterate, I'm running map2. And then the .x argument, we're providing the file names, that vector names. To the .y argument, we're providing that list of data frames from the experts output. So right there, we're saying it's going to be iterating and passing things to the keyword append function. And because that third argument that needs to be fulfilled is metadata, we just provided that final version of metadata that we had already selected for the columns of interest, so desired metadata. All these together get written out, and this is how we end up having expanded data frames, which is what we're going to have it return this particular data frame list to us, containing the additional keyword values appended to the original experts matrix data frames for each specimen. So, Concatenate should now be able to set up to retrieve and append the keyword columns to the individual data frames. So let's go ahead and refresh our function to make sure all those changes are made to our local environment, and then rerun the output line just to make sure we're actually getting back what we're kind of expecting. So at that point, you can see I'm keeping all four of the metadata column names for this argument. As I'm running it, if I check data, I can see I'm still getting back 3 individual items, which makes sense given I've specified return to me a list. But then if we actually use our square brackets and then go ahead and break into that first data frame, we can see all the column names of experts are there, but now we also have those keyword columns that we were interested in appending on that are going to be specific for that particular individual. So, woo, we have made substantial progress through the initial mental sketch plan that we had at the beginning of this walkthrough. So, with those individual experts data frames now having been updated with the specimen-specific keyword values so that they are now distinguishable, we are safe when it comes time to actually concatenate them together into a single larger data frame style object. So we can go ahead and do this by passing that list of data frames to the dplyr bind rows function, which will remove the list formatting and then just combine them together into a larger data frame. So what this would look like in practice, we're running all the way down. As you can see, we're getting back our intermediate expanded data frames list object. We're passing that to bind rows. It's going to combine them into a bigger combined data frame, which is what we're going to have returned to our local environment. So once again, as has been similar, rerun, refresh the function, run the output line, make sure everything is making sense. So since everything is now in one data frame, we can always go ahead and pull the name keyword columns and basically try to identify out the unique values that are present once we have 3 specimens to start. So what this is, for example, going to look like, if I pull for that combined data frame, if I pull for the name column, and then I just only keep the unique entries, because remember, there's over 6,000 if we combine 2,000, 2,000, and 2,000 from each specimen, you can see we have 3 unique values that are present within this column name. So, if we are only planning to work with the data in R, we could leave concatenate function as it is entirely and call it a day. However, since we are all cytometrists, getting this concatenated data frame back into a fully compliant FCS file is likely our targeted end goal or desired outcome. Consequently, let's check back on our starting notes and be better able to plan what our next steps are going to be. So, with these additional columns now present in our concatenated data frame, we will need to get these back into an experts matrix format. That will require converting any character strings to numeric values, which also means we would need to create a new keyword Within our description list, that would contain a dictionary lookup with a column corresponding to the before value and another column that corresponds to the after value, so that if we ever bring these back into R again, we can revert them back to the original style character string before they got converted into numeric values. Likewise, any new expers columns would require updating the parameter slot data frame to contain new rows, which would be designated by the row names in the, and this is where it looks like the slides went a little crazy. Basically, if you remember back to week 3, we had the $P certain number style formatting. You just want to make sure that as you create those new parameter slots, new rows in that parameter data frame, that if you're at P30, you would continue on for the next number, P31, P32, $P33, all those different keyword components also get updated respectively. So, since we are trying to generalize our code, basically avoiding any hard coding, let's start by first differentiating what data frame columns were added versus which were original, using both the olive and the select function to subset for or subset against the column names that were specified within desired columns. So what this is going to look like is we have our combined data frame, which is where we were leaving off on. We can then basically use select and olive to grab the actual metadata columns that we specified, which is going to be the new data. And then using that little exclamation sign to basically negate it, we could end up isolating out all the columns that correspond to the old data. And then at that point, if we check the new data when it's being specified as a return object, you can see we're getting back these 4 columns, which is what we're expecting. And vice versa, if we check for old data as the return object, we would see it's just all the expers matrix column names at that stage. So we can now start planning ahead for a new helper function that would help us go from character keyword columns over to numeric containing keyword columns. So in this case, we'd want to be able to iterate through each individual new column, i.e. that's what is being defined by desired columns. We would first need to evaluate whether the column is already numeric, because if it's already numeric, you don't need to go ahead and convert it back again. And then if that is the case, we could just skip to the next column. If it's not numeric, basically if it's a character or a logical type column, we would need to be able to provide a substitute numeric value for each unique value that is being present within that combined data frame column. So let's go ahead and start this new helper function. Let's just go ahead and call this one column to keyword, and let's write out that initial functional skeleton just like we've done for the last couple. So as we think about what does it actually need to do, we would be iterating in the new columns, i.e. those that are present within new data, through the use of their column name, which is being designated by desired columns. So we could use the same kind of internal arguments that we've seen in the past, namely a x and a data argument that could be used to filter for our particular column of interest. So what this is going to look like is we're just, again, internal function. So I'm just going to give a little brief description, the 2 little arguments and what they do, and then any function I end up using internally, I'm just updating the documentation for the oxygen just to make sure it's able to run once it's present. So dplyr, we're using select, tidyselect, we're using olive. So as we mentioned, we're passing in the data, and then we're passing in the name of the column that needs to be isolated. Since this name is a external vector, we just need to make sure to wrap it in the olive function from tidyselect to make sure it works properly. And at that point, we've isolated out a individual column that can then be worked with. So at that point, we could do a conditional, where we can basically check to see if that column that has been extracted is actually numeric, or if it's one that needs an intervention from our end because it's a character or a logical, and then be able to handle subsequent steps depending on what kind of answer we get back from it. So if we are setting up our conditional, once again, basically is numeric. If you're checking the individual column that we've isolated and checking to see if it's numeric, if the value comes back as true, this little exclamation sign is going to flip it, so it's going to come back as a value of false. So at that point, it would skip down to the very next one. So at that point, since it's actually a numeric column, you can see the message in this case, when this line of code gets run, it'd be it's a numeric would be skipped at that point. Vice versa, if it's not a numeric column, the is.numeric check is going to come back as false, but then at that point, the little exclamation sign is going to flip it to a value of true, which means all the content between these little curly brackets is actually going to be run. And as you can see, I'm doing a little message, darn, it's our problem now, meaning we need to make some additional adjustments. So as you're setting up a conditional, just remember, you want to make sure that whatever code you're specifying ends up in the correct conditional statement little curly brackets, and that you're not mixing them in the wrong way, in the wrong order. So this is one way as you start to build out the skeleton, just to make sure everything's working properly. So with this conditional setup now in place, we can start filling in what to do depending on the outcome that's being specified, depending on whether the column is numeric or not. So let's first tackle the scenario where is numeric comes back as a value of false. So we should first, at that point, it means it's going to be a character or a logical value. We should identify out how many unique values are actually present, because if we're turning these into unique numeric identifiers, this is going to be an important step. So, in the case of it is a character or a logical, this is going to be evaluated as true. And as you can see, we're taking that individual column that has been retrieved, we're pulling out whatever particular column name that is, basically turning this into a little vector list. And because these are likely going to be the however many thousand duplicates of each other, we're just going to set it as unique just to get out the actually truly unique values that are present within that column. So once you have those unique non-numeric values, we need to kind of create some numeric stand-ins for them. So typically for keywords that get visualized via commercial software, we also want to provide enough space between them so that we're able to gate them safely. So if you use something like Flojo in terms of commercial software, oftentimes you'll see they're like roughly 1,000 units away from each other, plus or minus a little bit of noise, just to make sure they're able to visualize properly if you ever select the keyword and visualize it on like the X or the Y axis. So basically what we could try doing is we could create a new vector, i.e. the values underscore key vector, that would be the same length as our original values that are unique, but just increase them sequentially by 1,000 to kind of use as a stand-in. So at that point, we could combine values and values key together to create a new data frame or a tibble function that could then serve as our dictionary lookups in the future if we're trying to go back and forth between the keywords. So in general, tibbles and data frames are very similar objects to each other. They're different in some of their behavior, as is mentioned during the link. So what this is going to look like is once this conditional statement is satisfied, and we retrieve out the unique values that are present for that particular column, we're creating this new tibble where we're putting in this case, those 3 unique values for names. And then for each of those, we're creating unique numbers to correspond to them. And basically, we're running the seek function, which is sequence. So starting at 1,000, increasing by 1,000, out however many times. In this case, length of values is the length of tree. So the values would be 1,000, 2,000, 3,000, respectively. But as you can see, none of this is hard-coded. It's going to be generalizable, and it's going to work regardless of if you have 3 unique values or 20,000 values, it would still come back correspondingly. And at this point, this object is going to be returned to the dictionary style object, which is what we have right here. So at that point, we have the original character or logical style values, and we have the corresponding values or key that goes with them. So ideally, we want to substitute in the actual column name that's currently just being held within the X object inside the function, so that as we iterate out, we're not just overwriting existing new metadata columns as new column value key, and then on the next iteration, rewrite value and value key by accident. So if we're able to swap in the original column name and then have original column name and then original column name underscore key, it's going to be much easier to utilize. So we can do this via the use of the gsub function. Use of the gsub function, and see if it actually shows me the code. Let's see. So as I scroll down here, you can see once we get this little dictionary tibble, I'm basically substituting in for the column names of dictionary, so which would be something like values and values key as it currently appears. Basically, X is going to be that original column's name, so anytime it sees the word values, it's going to replace it with that original column name. So in this case, let's say we use condition was what was being assigned to X. This is going to be column condition, and then column conditions underscore key would be the return that would get back after running gsub. And that would re-update the column names of dictionary, so that way as we iterate through and add additional columns, HEU status, infant sex, name, it's not going to overwrite those two shared column names. And make sure I covered that correctly. Yep. And then as you can see here, I'm using a return dictionary just so that we're able to check to make sure as we are running our lines of code that everything is actually being correctly updated. So as that's being parsed and returned to the dictionary tibble, we can repeat this process for the equivalent numeric columns just to make sure that we are skipping across and then we're not having anything get away from us if it was provided as far as values or values key correspondingly. So handling that condition of if we're expecting this to be a numeric column, we take our particular column that had been isolated, we pull out the unique values, and at that point we just have them write out values, but then because this is numeric, we also have values underscore key also provided the same value. So at that point it'd be like 1000, 1000, 2000, 2000, 3000, 3000 on two separate columns, just to be able to have the same exact format of what we would expect to be getting back if it was a character or if it was a column, just so they're compatible with each other. So at this point, the code for our column to keyword helper function is pretty much complete, so we just need to integrate it in within the concatenate function, passing in our new data column sequentially and ending up with a list of dictionary lookup tibbles that can subsequently get added into the description/keyword list slot. So as we are scrolling down, you can see we have got our combined data. We isolated out what was going to be the new columns in that combined data frame. And then at that point, what we can do is we are iterating through the desired columns, which correspond to those column names. We're passing that object to the function column to keyword, and we're having it iterate through the new data frame we have here. So at that point, each of those new columns that are contained within new data get checked. If they're numeric, you're getting back a keyword value that matches itself. If it's a character or a logical value, you get back a new dictionary lookup file that will have the corresponding numeric that can be used to convert back and forth accordingly. And this is what this is going to look like. So for example, when I'm running and checking that first one, you can see the first dictionary lookup. It has name, and then it has the name underscore key column, and you can see there's numeric values that are going to be used to internalize, and then same on and so forth. So as we now have the dictionary translations that are needed to convert back and forth our non-numeric keywords to numeric, let's start gathering some of those other components that are going to be needed for the final FCS file before we actually go and translate over the corresponding columns in the expers to the data from their data frame to numeric. So rather than try to create an entire FCS framework from scratch, it's often far easier to just go ahead and simply copy the contents of parameters and the keyword slots from one of our specimens that's already within the gating set, and then just subsequently modify the outputs that are needed so that it's not confused for that original file. So since that underlying data we will retrieve will vary depending on which FCS file in our gating set is being selected, we should provide an argument. In this case, I'm going to go ahead and call this one specimen index that will allow us to designate which specimen to use for this purpose. So in this case, we are added a new argument. So it's going to go here in our oxygen skeleton under @param. So you can see for specimen index. Any updated functions as far as they're being used get put in under the @importFrom tag. And as I scroll down, you can see here, we're starting to do some of that retrieval of metadata as far as what's needed. So we still have our gating set. When we use square brackets and we provide the index value, it's going to grab that corresponding specimen. And then at that point, we can go ahead and designate what's a subset we're grabbing, and then the inverse transform arguments that we would expect to be using in that case. And we're using the flow workspace gspop get data, retrieving out that initial cytoset of whatever gated population for whatever interesting individual we are designating. So once we have accessed that correct specimen, we need to make sure to retrieve the underlying data via flow frame, i.e. keep it in active RAM instead of the cytoframe, i.e. which is being accessed by the pointer, so that we're able to copy and modify the components, kind of like what we saw back during week 9. So what that's going to look like in practice is events in the gate is going to be a little cytoset object. When we take a cytoset and square brackets warn it, we are going to jump it down to a cytoframe normally within the flow workspace package syntax. But we also have the option of specifying return types equal to flow frame, which would just go ahead and directly load it into RAM as a flow frame instead of that intermediate cytoframe set. So at that point, we have a flow frame object. Everything, all the contents, all the metadata, the expers, etc., is present in RAM. We can then run parameters in the keyword helper functions to retrieve out the original parameters and the original keywords description lists that we're going to then modify to fit whatever our needs may be. So at that point, if I go ahead and double check just to make sure we haven't gotten too far out over our skis, you can see I'm getting back an annotated data frame when I'm specifying my return type to be the original parameters, which is what I'm expecting, and similar story for the description list if I wanted to. So let's step back, let's see where we're at. At this point, we've retrieved the contents of the original parameters as well as the description keyword slot for a designated specimen within our gating set. And we have them stored as variables within the environment of our concatenate function. So let's start turning our attention at extracting the dictionary lookup tables from their list and then integrating them in as new keywords within that description keyword list we've just retrieved from the specimen. So you may think this might be more complicated, but the process is actually quite simple. So namely, we just need to flatten one level of the list layering, which we can do with functions kind of like flatten from the per package, at which point combining on these additional keywords into our original description keyword list can be entirely accomplished through the use of the little c, i.e. the concatenate function from base R. So what that's going to look like is as I go down, you can see here, we're down here at the point where we have the dictionaries, which are going to be the lookups of the original versus the numeric equivalent values. I'm just going to flatten that list to get back to our keywords, which I'm saving as the new keyword value. And then I'm just appending those onto the original description list through the use of C as far as the function. So this is now being saved as new descriptions, which I can then return. And then if I check the very last part of the description list, you can see what I've associated normally to be the end keywords for our FCS file, but you can see I have name, name key, condition, condition key, infant sex key, etc. So I'm able to go back and forth based on these internalized keywords if I need to. So our keyword lookup dictionaries are now present in the description keyword list variable, where they are being used to convert and revert back and forth from numeric to non-numeric values as needed. So with these dictionaries now safely stored away, let's go ahead and proceed to convert over the values that are currently within the experts data frame from their current non-numeric values to the matrix appropriate numeric values we've been trying to get to be able to utilize for the last 30 minutes or so. Which of course means we need one more helper function. So to start this conversion, we're going to need to retrieve the dictionary lookup tables, which contain our paired unique original values column and the numeric equivalent values key column, and then our data frame, which is where we're going to convert the corresponding column to translate it into the numeric appropriate keywords that need to be used when you're internalizing it to a FCS file. So, while an iteration approach for each column could be attempted, in this case I chose to implement a for loop, which we briefly covered in the past, within a new helper function keyword translate to be able to handle this conversion. So consequently, only 2 arguments are needed for setup. The dictionary list containing those matched key and numeric key values, and then the data, which is what we want to translate over so it's integrated into our flow cytometry object. The for loop basically will iterate through the names of the first and second columns to then be able to do the corresponding namings accordingly. So what does this actually look like in practice? So we have for the given entry in the dictionary list, which is the dictionary lookup, which would have a data frame of 1 column, 2 columns. You can see it's identifying the name of that first column, names of entry, grabbing the very first object, assigning that to the value column name, and then same thing, names parentheses entry, second index is going to be the actual key name for the corresponding value there. So that's just our intermediate. So now that those are being retrieved correctly, we can just go ahead and proceed. So remember, what we're going to basically do is try to merge these together through the use of the left join function. Let me try that one again, blanked a little bit. So with the names of the original and the key columns in the dictionary list object now correctly retrieved, the new column experts data frame as well as the dictionary list tibble are able to be merged by basically piping together the left join on the basis of those original column names. At that point, the original column can then be removed, leaving only the numeric key column, and the leftover key column could then be renamed so it now matches the original columns, basically swapping into place the numeric value in place of the original character style value column. At that point, that would complete the substitution in of the numeric values through the use of that for loop, repeating for each corresponding dictionary item that's being used. So what this is going to look like is within that for loop, after we have the names of those 2 corresponding columns within entry, you can see we're joining our data, which is the original big frame. We're left joining it to entry by the use of column name, since they all match each other on that first column. At that point, we're piping it in and removing column name. And at that point, the only extra column that has been added to the original data frame is the numeric keyword value. At that point, we're basically using the rlang packages rename in place syntax, which is a little bit complicated. You can see the code line there, which basically renames the keyword, the key name column to be the same original name as what had been present before. So swapping it in place. So if this is a little confusing, just play around with this with your own set of data. This is where it comes in as far as the substitution goes. So at that point, if the for loop is running, it's going to iterate through those dictionary lookups, and any corresponding column that matches that first lookup column name will get translated into the equivalent numeric value. So at that point, everything is now converted over to numerics. It's able to then be integrated into an experts matrix and then is able to be utilized within the actual FCS file. So let's go ahead and actually add this new helper function and actually integrate it inside Concatenate into our growing function as far as we have. So as you can see, basically we are flattening the dictionaries list to just get at the new keywords. These are being added into the original keyword list. So at that point we have new descriptions. But then in parallel now, we're going back to focusing on the experts matrix. So we're taking that new data, we're passing it those dictionaries. It's going to go ahead and numerically translate over those originally character columns, which is where we get this translated new data frame. And as you can see, if we now check for the data frame and we're checking the name, the condition, the infant sex, and numeric, you can see there's over 6,000 rows. They're all 4 variables, but you can see the corresponding numerics are now present, not the original names that were in character style strings. So at this point, we've made changes to both experts as well as the description slot. So let's just go ahead and assemble the components back together into a new flow frame object before we actually try to tackle the last component of updating the parameters data frame. So at this point, we can start by converting both translated new data and the old data frames back together into a matrix format. Then we can bundle old data, original parameters, along with the modified new descriptions together into a new flow frame style object. So what that looks like in actual practice, putting everything back together again after having truly dismantled everything. Translated new data is everything in a numeric form. We're converting that over to a matrix. Then we can do the same thing for the old data, convert it back into a matrix. And then when we create our new flow frame, we're still keeping the old matrix in terms of its original values because we haven't updated parameters just yet. We can still keep the original parameters, but we're updating the description keys to include all those new values that we ended up incorporating. So at that point, we have this as a new flow frame object. And sure enough, if you scroll down, you can see no new particular values, no new particular parameter data frames are present. It's still showing these guys, but the keyword says increased compared to the original version, and we are still downsampling correctly for what we're trying to grab. So, at this point, we're at a little bit of the calm before the storm. So, as we look at the flow frame output, we can see that the Expers has updated the flow frame print to show us that 6,000 cells are present. Likewise, the description list now lists those 480 keywords. However, we still very much have the old parameter slot with its quirky little p certain number style naming format, as you can see right over here on those row names. And each of these is increasing sequentially by 1 as additional new Expers columns get added across the board. So, as we are thinking back to that starting mental sketch, we now know we need to basically take those new keyword columns that we've added in, and we should add in a corresponding p-value row within that parameters data slot. Ideally, beginning immediately after the last entry that's there, which I think was P43 for that particular column. So, as we explored back in week 3, we also remembered that those P30 style row names, there are several description keywords that are present within the keyword slots that basically will correspond to the voltage, the range, the name, whether it needs to be displayed in linear and log. All these are particularly important, especially if you want to minimize issues when it comes to our concatenated SCS files and their ability to interact with commercial software. So, we need to build out another helper function. So as you can see at this point, we are several helper functions in, and we're still getting towards the end, but we haven't fully assembled Concatenate, which is the main reason why this was put into a bonus walkthrough, and we didn't try to fit it into the week 10 workflow as far as things go. So yeah, at this point, we need to do a little bit of cleanup with Concatenate. We have 2 existing objects within it. We have the reassembled flow frame, new FCS, as well as that new data matrix that we want to basically be able to put into Expers, but we first need to make sure to update the parameter slots and the keyword slots to reflect this. So let's go ahead and tackle the last major hurdle. So we need to be able to update those parameters. So we're going to do a little helper function for parameter update. So it creates those arguments that can then be used as inputs for our function. So what this is going to look like is, once again, internal function designated as such in the oxygen. We're going to be passing the flow frame, and we're going to be passing it the new columns matrix that we want to be incorporated in. Our first order, especially if our goal is to generalize the new column integration as rows within the parameter data slot, is to identify how many columns we are already working with, what their names are, and what existing rows are present within the parameter slot. So, if you're looking at this right now, if you're checking new columns, that's just literally the matrix object containing the new metadata numeric columns that are going to get added. We can find out how many there are, we can find out their names, and then we can also check within the parameter slot of our flow frame object by running pdata we get at the data frame. We can find out what the existing data is for the parameter slot. So at that point, we just need to check the row names and basically identify which was the very last $$ style row name that is present, and then just basically use gsub and go back and forth to make sure that we're aligning it to be the next particular value. So the way we're basically going to be able to do that is, once we get the row names, we need to be able to remove the $, which is going to cause a lot of issues when it comes to trying to arrange it. But then at that point, convert over what's being seen as a character value in R to a numeric, run the max function on it to identify what is the max value that's present. So like P43 would come back as 43, etc., etc. And then at that point, we just need to add a single value on top of that, which would be our new starting value for the p-values for our new Expers matrix columns that get added. So at that point, we're continuing on down here, basically this section of code here. So basically, it's checking the row names of the old parameters, and it's being used within gstub, basically getting rid of anything that contains $p. And then at that point, we're passing it to the asInteger function, which is converting it into a numeric value. At this point, if we're evaluating this line of code here, it identifies the max numeric value that results from this, and we're adding it a single value of 1. So that is the new value by which we would need to start in terms of column numbers. So with that identified, we could then extend the sequence out via the seq function to the length corresponding to the number of our new columns. So let's say if we had 43, but we have 4 new columns, it'd be 43, 44, 45, 46, and so on and so forth. And then at the end, we just need to modify this vector by pasting on the $p that we had removed, just to make sure it's following the same syntax as the other row names. So as we look at this being implemented, we had those new parameters, we identified what the max value was, we're doing a new sequence out to match the corresponding length of our new columns, and then we're modifying this back to a character kind of structure, and then this is being returned from return. So at that point, we would have the equivalent number of row names that are needed for adding in to the parameter slot. We would just need to be able to specify also the name, the description, the range, the min range, and the max range for those corresponding ones accordingly. So at that point, a lot of what you're going to see in this next function is code that gets borrowed from the original Flowcore package. We had a base R implementation of the process. So if you want to know a little bit more about how base R does iteration, it is namely generally through the apply style functions. So apply, lapply, sapply, vapply, papply, etc., etc. They are functionally similar to map from the per package. They'll iterate through a vector. That name as it gets iterated through could then be used to subset to the according column, and existing numeric data used for our column could then be appended as well. To designate out a range and min-max range values, etc. Let me try that again. So, base R's lapply is able to do something similar to iteration for map, iterating through the new column name vector. This name could then be used to subset the correct column, to which we could add existing numeric data to calculate out the range and the min-max range for the underlying data sets. And then this could all be reincorporated together to become the parameter data we're associating with it. So in combination, oftentimes with base R, you'll see the doCall function, which is used in combination with rbind to bind all these outputs together into what ultimately can become a single data frame. At that point, we just need to modify in the row names by passing it our vector of the different $p value vectors to make sure it is matching the same kind of syntax that we're associating with pdata. So let's see what that looks like in base R. So we are running lapply, which is our iteration through the new column names, and it's being passed to a function that's getting written in place. So remember, the vector is basically isolating out that original underlying data from our matrix, and then we're running range function on it to see what the actual range was in a numeric kind of style value. And then we're creating this little internal data frame where the name is that thing we originally iterated in. Description is normally the antigen name. There's no antigen name in this case, so we can leave that empty. Range, basically, we can see the actual range plus or minus the differential, just to see how far across it goes. And then we can specify the min, the max by breaking these accordingly. All this then gets passed to doCall and rbind, which cobble them together into an original data frame. So as you can see, you can do this in base R. It's just a lot more complex in terms of the syntax, which is why for this course I've been kind of preferentially going for the dplyr packaged version of this. Ultimately, this updated parameters, we just are refreshing the row names by providing those $p's, and then at that point we now have an updated parameter list that can then be added on. With this process complete, we have basically retrieved the new data frame rows that need to be added on to the original parameters so that we're able to successfully integrate in the new experts columns when we create the new FCS file. So let's go ahead and run parameter update with inside our concatenate function. And as we start scrolling down, we can see that here we're running it through our helper function, passing it that assembled FCS file, and then the new data columns that need to be added, and this is coming back as a new parameters object. And sure enough, you can see we have name, condition, infant sex, HEU status, starting at 44, 45, 46, 47, as should be the case. You can see the description is empty. You can see the actual range of these values. You can see the min range, the max range in terms of the numerics that are associated with each. So at that point, we can go ahead and safely combine in the new parameter values onto the old existing data to make sure everybody's accounted for within that parameter slot. So at that point, we could use either our bind or bind rows, depending on what we're trying to do, and then that would be able to be added back in, overwriting the previous one, and making it able to account for the additional columns that are present within Xpers. We can also similarly do the same thing by adding new numeric keyword columns to Xpers slot before passing it to the new FCS file as well. We can access this new Xpers slot through the use of the @ symbol as we've encountered in the past. So at this point, we're reassembling the new updated one to be correct for both the parameters and the Xpers slot. So at this point, we're extracting out the original parameters. We're binding those original parameters with the newly assembled ones we cobbled together through parameters updates helper function. And then this one here, at that point, can then be applied directly to the new assembled FCS file. But before we do that, let's just go ahead and cobble in the new Xpers matrix, the one with the new additional names. So at this point, they're matching each other in terms of total number of columns and total number of rows, which would correspond to those one by one. And then at that point, we can return the new FCS file, which should be updated correctly across the board. And sure enough, at this point, we can see we have 6,000 cells, but we now have 47 columns. And if we check the P data, we can see we're up to P47, so we have successfully updated the parameter slot. Alright, now all we need to do is basically for those last few P row numbers that we added, we need to add in the necessary P-style keywords to the keyword description list so that they're fully compatible with the commercial software. So, since we had calculated those out via parameter update, we don't have that information as a vector within the concatenate function itself. So consequently, we're going to need to retrieve the row names and the keywords so that we're able to have them available when it comes time to editing. So what this is going to look like, scrolling all the way down, you can see we have that intermediate parameters data frame there. We can run row names to get out those new values. And then same thing, we can run the description slot off the new FCS to see what the keywords are in the current status before we start adding in all these parameter-specific keywords. So now that we have access to those, for basically every new $P row name that got created, we need to generate the respective keyword variants so that we can integrate them in together to reflect correctly in the description keyword list. So the easiest way to do this is basically to write a for loop. And as you may remember back to week 3 when we did deep dive description keyword lists, there's all these little weird variants that are oftentimes instrument manufacturer specific, like B, E, N, R display type, as well as a couple flow core ones that get created when there's transformations are being applied. We need to create all their equivalents and place the stand-in values just so that they're recognized as proper parameter values by the commercial software. So, I don't remember the exact origin of this one back in the day. I had encountered it probably while deep diving this in the first initial attempt, and this is the code that basically works within the for loop. So remember, each of these is the new P number certain value. It's basically within the for loop, it might be P43, P44, P45, P46. It iterates through them equivalently. But then from the new keywords, which you may remember is actually being a list object, it creates a new one, and then appends the corresponding values. As you go down, there's like voltage, there's like linear, what identity it can be, all this little bits of more minute FCS cobbling together happen to be able to make sure all the equivalent keywords get created on a per new row basis. At that point, you had successfully assembled expers, you successfully assembled the parameters, and you've successfully assembled the new keyword object together. It's time for that last push to just assemble them into a fully integrated flow frame object. So at that point, scrolling all the way down, you can see parameter slot is updated, expert slot is updated, this new keyword list is coming back updated after we pass this for the for loop. They're all being plugged into that new equation to create us the updated FCS file, properly containing all the formatting needed for those new metadata columns that have been incorporated in. And sure enough, at that point, if we check, we have 555 keywords, we have the proper number of p data rows, and then we have corresponding expers of what we're expecting to see. So, congratulations. After, I don't know how long, hour and 40 minutes, we have a fully modified flow frame that we're able to integrate in the keywords correctly. So all that really remains is just a little bit of a minor cleanup. So at that point, with our new flow frame assembled, all those metadata columns placed in correctly, we just need to make a few modifications to our desired keywords, allowing us basically to tell apart the concatenated file from that original source file that served as the original donor for all the formatting for metadata, keywords, etc. And then at that point, we can borrow some of the code we had in downsampling that allowed us to basically dictate, do we want our return type object to be a data frame? Do we want it as an FCS file? Whatever the case may be accordingly. So as we go scroll down to the bottom, you can kind of see the little things of changes that can be done. So this is the newly assembled flow frame. We can assemble a new name by providing an external argument for file name. Like, let's say I wanted to call it my concatenated FCS file. I would just provide the value to file name. Vice versa, if I wanted this to be infant 102, I'd provide that value to file name. And since it's being designated externally in the argument line, it will go and actually be applied. At that point, similar to what we did for downsampling, we can end up overwriting the existing GUID, the existing fills, just to make sure that these are distinguishable as the concatenated file, then they're not going to be confused with the original file, or accidentally end up overwriting the original file. And then we do all this little extra code that we've been doing in the past, basically saying if there isn't a location specified for storage location, just place it in the working directory. If there is, this is going to be your write out path. And then based on what return type argument we provide, it's either going to be written out as a data frame, it's going to be written out as a flow frame, or it's going to be written out as an FCS file. So that way we have flexibility of how we get back our concatenated file. And sure enough, let's just go ahead and double check. So our brand new assembled concatenate function, if I set return type to FCS and I hit run, we end up finishing everything we need. So at that point, the process by which concatenate has been written, and we can see how it's implemented within the workflow. So at that point, we can go back to check for the week 10 walkthrough. So first off, congratulations. After long last, you made it through this extensive walkthrough. So as you can tell, FCS internals, as implemented within a flow frame, are very much not for the faint of heart. There are multiple moving pieces across 3 slots, and a small army of helper functions that's required for the interconversions. However, there is value in at least understanding the basic ideas and the interconnections that are being made between them. So in the current implementation, everything remains connectedly matched, which allows those FCS files that you generate to seamlessly switch between R and the commercial cytometry software without taking a performance hint that needing to reset the transformation and scales accordingly. Additionally, the ability to encode important information on a cell-by-cell basis, as well as back-translate from the description list, will prove immensely helpful later on when we kick the tires of various unsupervised analysis algorithms and try to determine how they actually work behind the scenes. And with that, that's all I have for today. Thanks for those of you who attended this recording of this bonus walkthrough. I know it's off the regular sequence. If you have any questions, I'm going to be here for a few minutes, and if not, I will see you next time. I'm going to do the other two recordings for today, starting in about 15 minutes and an hour afterwards, respectively.